Yeah, so this afternoon and probably for the next couple of days as well, I'm going to be talking about metaprogramming and specifically about one aspect of metaprogramming, which is how tactics work. So we've seen quite a lot of tactics so far. So the tactics are the main keywords that appear in your proofs that that sort of lead each line off and which explain, what's going to happen in that line. So I think we've seen many so far. Just to get you thinking along the right lines, you've seen intro and have and obtain and apply and rewrite and ring. All of these are tactics. Anyone remind me of a few others that we saw last week? Use. Ring normal form. Omega.
Induction.
Yep.
Constructor.
Smash. Is it? Oh, yeah, sorry, I was thinking of smash. That's a new one. Right. So, you might feel at this point, what was that?
3 more.
Yeah. Well, there's tons more, but you might feel at this point that this could go on forever. But in some sense, compared to the rest of the aspects of Lean that you have to learn, this is a pretty finite thing to learn. There are probably, this is a list of 15 or so. Probably, like, by the time you get to the 40th most used tactic, you're getting into things that you use rarely and nobody else ever uses at all. So I would say the number of tactics that you need to know is on the order of 20 to 50. It's like an alphabet rather than a dictionary, which is what the complete set of all of the theorems in the library amounts to. So what a tactic does is it puts together theorems in some sort of predictable way, and somehow it takes, a tactic is a thing that works in many different situations and that brings in some lemmas that might change from use to use to build together a part of a proof. And this might sound very mysterious, and the idea of these lectures is going to be to demystify that a little bit, to talk about what some of these tactics are doing when they build a proof for you, what that means. So this is not a topic that is traditionally taught to people who first touched Lean a week ago, and therefore it's a bit of an experiment to try to teach it in this context. If, after half an hour or 45 minutes, you're totally perplexed and bored, I will not be at all offended if you just go out into the other room and start, working on something else. If you want to interject and lead me on a tangent that you think is more relevant to what you actually understand, that's also totally fine. This is a bit of an experiment to teach this to people who are effectively beginners, and I hope it works out, but I think we should also be free to experiment. It's also all Alex's fault. He was the one who suggested that we try to teach this. So, complaints to him.
Blame.
So I think in our first session today, we will probably not get around at all to building tactics. Instead, we're going to think about what tactics are doing. So if all goes well, by the end of our 3 lectures, we'll have rebuilt the so-called interval cases tactic, which is one that we did see last week in one of Antoine's lectures. And let me remind you what this interval cases tactic does. So, So let's say I've got a problem in which I'm given a natural number, k, and 2 facts, that it's at least 1 and that it's no more than 4. And I want to show that it's a factor of 12, which happens to be true if you think about it. How might I go about solving this problem? The first step I might say is, because k is between 1 and 4, there are 4 cases, namely k could be 1, 2, 3, or 4. And so you want to be able to do a case split, and that's what this interval cases tactic does. After I run interval cases, on the right, I have 4 goals, showing that 1 divides 12, 2 divides 12, 3 divides 12, and 4 divides 12. So this is a very natural sort of operation to want to perform on a proof state, the state of taking a bounded natural number and expanding into the cases that that bound implicitly corresponds to. This is the tactic I want us to build up to writing. I think it's neither too simple nor too complicated. It might actually teach us something. So what I want to do for at least the first sort of half hour of this lecture is to figure out how you would do this by hand. So if we were in the dark ages before somebody wrote the first version of the interval cases tactic, how would we do this? What on a sort of strict logical level involving various levels is actually happening here? Yeah.
Maybe you can somehow imply from the fact that k is between 1 and 4 that k is either 1 or k is 2 or like just prove this implication.
So that's sort of the end game, but I think I'm looking for more granularity. Like, what is Lean actually doing? Like, what could we do? Yep.
Maybe shrink the interval.
Maybe shrink the interval. I like that. Yeah. So maybe that's also where you were going with this. But shrinking the interval is a very good idea. And I think that's also where I would start. Like, maybe we can say either k is 1 or it's between 2 and 4. And then the problem has become smaller. And then repeat that process over and over again. And hopefully it will terminate when the interval gets to 0. That's a very plausible idea that draws on ideas of sort of recursion in computer programming. So how do we shrink the interval? That's the question. By half, okay. So tell me what I should write in my half.
And then half, meaning divide the intervals.
Oh, by halving, I see, okay, sorry.
Oh.
Interesting. So I think you're right that it might become a more efficient algorithm if I were to do this by bisection. But in practice, efficiency is not always the most important thing when writing tactics. I think the algorithm that maybe we were talking about before, where you sort of, have just building up from the bottom to the top of the interval, although probably slower, is just as good in this case. So I would propose that we work from the bottom up rather than splitting and splitting and splitting, just because the implementation will be easier. I think I saw a hand over there, yep.
Have h colon k equals 1 or k 1 less 1 at least k at least 4.
Let me skip the at most 4 for now and just write this. I missed one. K equals 1 or so this is in its current state. It's trivially true, right? Because we already know that k is at least 1.
2 on the...
Oh, 2. Sorry, I missed that. Okay, yeah. So yes, I agree. Like, let's suppose that we could establish this statement, and that's probably 1 lemma away. Then we can case split on that, and in the first case we have k equals 1, and in the second case we do the whole thing again, and we do the whole thing again, and we do the whole thing again until hopefully we stop. So yep.
It only uses h1.
So far. So yeah, we would keep on doing this, maybe at the bottom edge of the interval. So let me maybe draw a little picture. I've started with the natural numbers 1, 2, 3, 4, 5, 6, 0, and I started with a requirement that I be colored chalk. Maybe not.
No, outside.
Okay, next time. So we started saying we're working in this interval, and then we decided that we were actually going to work in this interval, in special case this one. Oh, great, yeah. And then, once we're dealing with this one here, we'll decide to special case 2, and then we can work with this interval. Then we'll special case 3, and we can work with this interval. then we'll special case 4, and then we can work with this interval, and hopefully when we get to a totally empty interval, we'll conclude that we can have some other logic to show lean that we finished off and there's nothing left to consider. So yeah, I like this strategy. So I guess all we need is a way of seeing why this is true. Let's see if we can find a lemma in lean establishing that fact. Oh, it doesn't exist. I think there is a variant of this. Let me see if I can remember. Maybe I found it before under the form 1 less than k. Yeah, okay. So since this is kind of a weird form of the lemma, let me copy it out in the form we need. So we're going to want a slight variant of this lemma. Maybe I'll call it theorem foo until I think of a name. It's going to say if I have 2 natural numbers and all the other conditions here, and and they were called A and B here, then either they're equal or A plus 1 is less than or equal to B. And that is a variant of this lemma, which I think is definitionally equal. Let me see. Okay, so let me explain what happened here, because this is a bit of a trick, which I think is kind of funny. The point is that in lean, natural numbers being less than each other is by definition the same as the first one plus 1 being less than or equal to. That's the definitional statement of being less than. So in the library, I mean, so these are by definition the same. And so when I didn't find the version I wanted, which was this version, the one that actually lets me go up by a step of 1 each time, I searched the library for this variant, which I was more confident in expecting, because this is true in any partial order. Namely, in any partial order, if you have x less than or equal to y, then either they're equal or there's a strict inequality. That's it.
What happens if you try exact question mark on foo?
I thought,
Because I think for now that you're written A plus 1, maybe it's there. I mean, it's surely there, something like that.
By exactly.
By
yeah, it doesn't work.
there must be something like that.
It's surprising to me that it doesn't, but I think exact, maybe is fast. Well, it hardly matters. Anyway, so I'm just going to take this slight, adjustment of this lemma to our circumstances, which really makes explicit the plus 1. Maybe I'll call it something better than foo. Let's see. Eq or suck LE of LE maybe is a good lean style name. And I will make these arguments implicit. We haven't had the implicit versus explicit discussion yet, but ask me later. And now I think that is just this lemma applied to this hypothesis gives, and I actually want the 2 less than or equal to version. Okay.
If you put LE dot, if you put the proof of line 20 at line 27, would it not work?
It would, but I really want it to have the plus 1 sticking out. So what we're doing here is we're taking the A less than B, changing it explicitly to an A plus 1 less than or equal to, so that the tactic becomes sort of transparent in some way. Okay. So the idea is that I'm going to case split here, and then I'll repeat all again. Anyone remember how to case split when you have an OR statement?
Knows 1 plus 1 is 2.
You're right that if I was being really careful, I could say 1 plus 1. But I think it's true. I'm not sure if I know a good way. Okay, let's see. I think it's true that 1 plus 1 equals 2. By definition, that's what this RFL means. So yes, by definition, 1 plus 1 is 2. They are syntactically different, but definitionally equal. Okay. So yeah, I was asking what I should do with this nice OR statement that I've built up and called H, and I was soliciting ideas on that.
Or cases.
So I've heard in R cases that will work. I've heard in match. I think the match will not work here because it's not. Maybe it would because it's secretly an inductive type. But let's
I underscore cases.
By underscore cases will not work because we really want to split an or that we have here rather than a case split on the truth or falsehood using the law of the excluded middle. I heard our cases, but I personally use the almost identical variant of our cases called obtain just because I like the syntax better. So I'm going to do it with obtain rather than our cases. So anyone remember how to use either obtain or our cases on an or statement, what the syntax is? Okay, so the syntax is going to be something like obtain, h primed, vertical line, h double primed, colon equals h. And this splits into two cases. In the first case, I get a hypothesis h prime saying that k is 1. In the second case, I get a hypothesis h double prime saying that 1 plus 1 is less than or equal to k. Yeah.
Well, why wouldn't you just say cases H?
I could also do cases h. Yep, that would also be fine. And maybe I'll write the r cases version just so we can be completist. So if I wanted to do this using r cases, it would be r cases h with h vertical line h double. I think this works.
Is it necessary for
Yep.
the hypotheses have different names? Can you do?
It is not. I could keep calling them all h if I wanted to, for example. And then there was a suggestion I use cases, so let me try that way. Cases h with h primed h double primed. I guess that's cases primed. If I want to do cases, I think the syntax is like INL.
The yellow bar, the yellow bar does it for you.
The yellow bar. Okay.
Yeah, the skeleton.
Yeah. Okay. Great. I find the syntax very wordy, and I've clearly done it wrong.
Sorry.
Yeah, I find the syntax very wordy personally, but you're certainly free to use it. So any of these would be fine. I'm going to stick to my favorite obtain, but I'll keep the other there in comment in ghostly version for those who want to see them. Okay. So now in case 1, I'm nearly back to what interval cases did. It's just that interval cases went a step further, and rather than just saying that k was equal to 1, it also just changed all the k's everywhere to 1s. So let me do what interval cases would have done. And actually in the first case, furthermore, substitute, this is a variant of rewrite we haven't seen before, substitute h primed, which means, so this is a variant. This is a variant that says, change all the k's to 1s everywhere. And at that point, our first case really exactly matches what interval cases was giving us before.
Is substitute literally the same as like RW brackets H prime at star or something like this?
It's pretty similar. I think there are technical differences, which I'm not even sure I could call up on the spot, although probably someone else in the room could.
It's even better. It's more powerful.
Okay.
For example, it automatically deleted the equation that would become 1 equals 1.
Anyway, it really does not matter, but I think it's useful to think of this indeed as being rewrite everywhere. So now we've done the first case of interval cases. And what I will propose for everyone now is do it all again. So we have this implicit algorithm in our minds, which is that you case split as often as necessary until you have all of the cases considered. So please take a moment and pull up your computers and run git pull if you haven't run the git pull since earlier today. And do the next few cases as you bring the lower bound up and up and up again. And then I think once you get as far as the trivial case, the point where we have lower bounds meeting and we need to rule out anything more to do, let's get together again. So take a few minutes and see if you can fill in the next few steps of the algorithm we're developing here.
Can you say what subst does?
Yeah, so I think it's easiest to look at the before and after. So H is an equality. It says that, H prime is an equality. It says that K is equal to 1. And what it's doing is it's looking in the goal state for all of the k's, there's a k in the goal, k divides 12. There's also some k's in the hypotheses. We've got some bounds on k. So this uses the known fact that k equals 1 to change every single k into a 1. And then after I've run it,
Because it's
the k has completely disappeared. So
has H prime, because it's.
as has h prime because it's now trivial, yeah. So I think last week we would have written this as rewrite h primed everywhere, which is also fine. But as people were pointing out, subs is maybe even slightly cleverer.
Clear H prime.
And it knows 1 divides 12. It knows 1
Nope, it does not yet do 1 divides 12. That remains as a goal for us to prove. And this sort.
Done with this case.
I've left a sorry. So the sorry is checking that 1 divides 12, and I haven't done that yet. But we're not even, somehow we're talking about the manipulation to get you down to concrete numbers dividing 12. That's the tactic we're building, rather than the part that comes after it. Okay, so maybe show.
Tactics for that last bit.
I mean, I could prove that 1 divides 12 by saying, you know, use 12. Yeah. Anyway. You know, puzzle for the interested, what did I just do? But I mean, I think that's a distraction. So maybe can I get a show of hands who has managed to download the latest code? Okay, so if you have not yet managed to download the latest code, maybe put your hand up and some of our many experts can circulate and help you with your GitHub problems.
If we had n rather than 4, work.
No, this is a tactic that only works for concrete numbers. Yes. Anyone else need help with their GitHub? You're supposed to get this code here, which I pushed at lunchtime, and pull it to your computer. Oh, really?
Was angry at me.
The point is that what he was complaining about, that you modified something that she also modified. So
We're
just finishing that thing.
Okay.
That's a gut.
So what I did, I stashed that. Stash means
Maybe I'm missing.
like we did essentially hide the modification somewhere. So yes. So it was before we start working with it. Then I got
I expected this.
made by Heather. And then I said apply stash. That means okay, now
Go find the thing.
redo
Okay.
what I did. And if sometimes you say, okay, now there is really like this line, both of you modified it, so now I don't know what to do. But
several of us are
it's
having
not complaining, so it means that it was
file.
like everything you did.
But what we'll do in your case is we'll just.
So now you have the version.
Thank
So
you.
you probably do the same thing.
And then.
So it's
So I went
so
to the docs.
this is just one technique. There are several of them. You can, so there is this stash thing. It asks you for a message, you can just give an empty message. Now you take all the, so this is just all the just one. And then, so now it's like the repository online, and then you want to reapply what you
But
did.
like, this is like their time.
Stash, apply latest
And when I'm
stash,
not
that it means
helpful, I don't want you to.
rewrite everything.
But we're partway into it, we're not sure to do next.
I stashed.
So now,
Just
okay,
like
stash means
Yeah.
what you write, now it's somewhere else, so who cares? Now you want to do that is download.
Yeah, so I do click this.
Yeah.
Okay, cool.
Okay, don't forget. I stash.
No, yeah, I commented.
Well, I
how do you close this message in Vim or this like save and?
Oh, but I wanted to do it.
In Vim,
Yeah, this.
ask the Vim
Without
people. Vim is already
Right.
shift.
Oh,
Q,
no, no, you don't
left,
have it on
Q,
your.
whatever.
No, I did it like, no, it's all.
I use, now I go to.
I use
Stash.
There is-
Apply,
yeah.
stash.
I use
Yeah.
And then I'm trying to.
File
start-
in
No, no, but
Yeah.
you're just trying to.
Another solution is commit. I don't know if last week someone explained you what commit does.
I
or-
tried committing, but it wasn't, I mean, it was telling me to do a message, but I wasn't sure how to do
That
a
you have to
message.
stage before probably.
Okay, yeah,
No, but okay, I mean, this stash thing is basically the same. So
okay.
No, it's fine. You can push if you want, but no, if you will not use it, so it's fine.
I think it should be.
And you can, if you want
Now I have it.
some
Yeah.
just some suggestion, you can close this thing that you probably don't, I mean, unless you really want it.
No, you-
Yeah, and also the minima is completely useless. Like,
And you can close it.
how do I do right click on the Mac?
Oh, yeah,
Two
double,
Okay,
yeah.
and erase the minimum.
Thank
Thank
you so
you.
much.
I hate that. I'm just like, I guess this is what it is. I guess I'm gonna have a mini now. Where you were working before. Trying to learn different problems. So I've been working on the code space, but I've been trying to have it almost like space for a while. And then,
Oh, no, this is bad, this is bad.
Okay, so what's the problem? So there is an error, but it makes sense because these
Can we
error.
close VS Code?
Yeah.
I'm not able to use the Mac, but no, that's not, I really close it.
Okay.
So this is not VS Code, this is Safari or whatever, or
No,
Chrome,
this is VS
whatever.
Code.
Close VS Code, please. And now give me a terminal in.
Well, it's normal that you have an error.
This is already the
Error in the file, which was supposed to know.
So where is your?
You put a bullet on- oh, sorry.
Yeah, repeat and
That's fine. Then I don't know.
And it's gonna pull up like you were last time.
Let's try if it,
Oh, you could just put.
when it's not.
Oh,
So
Then you don't have any.
somehow it was what it was doing was compiling Mathlib. This should never happen.
Okay.
Sometimes it happens for strange reasons. Nobody knows why.
And then just super weak.
Yeah. And so what I'm telling him is to download a precompiled version,
Okay,
and then
okay.
this usually you have to click just once. So
Yes.
it's like
What is
30 seconds will be done.
Ah.
And it's better to do it when with VS Code closed, because VS Code also try to compile it
Yeah.
at the same time, and maybe the files produced by VS Code start
Anyone else need
conflict.
anyone else need a Git wizard to come and help them?
No, you should have no, it's fixed.
Okay.
I mean, I agree.
Maximum
Yeah,
recursion.
but this, I mean, this should compile at any rate. I mean, you should get to a status where the file compiles and there are errors. It's a bit strange. You can try to close on VS Code.
Let's just, there is really nothing necessary.
I guess it should be like until.
Yeah.
Using
So-
batch, like I suggested, would that be considered that style?
Usually like.
No, but that doesn't matter. It's science. Okay. So
Okay, okay.
Wanted to show ahead of time.
I'm
Now you
trying,
can-
one of my goals here is like to learn like what's like the meta, like what is considered good
Yeah.
style
Yeah,
versus
yeah.
bad style.
So that's a secret, what you just told us. Okay, so let me do one more case, just so that we can start to pick up the algorithm here. So I handled the one case, like modulo actually proving the fact. I got to case one being that I had to show that 1 divides 12. So now I'm going to do it all again. Anyone with a suggestion of what my next line should be?
We have H2 is K equals 2 or K is bigger than.
I think I've got an H2 name taken, so I'm not even sure what a good naming convention is. Maybe I'll call these big things that I'm splitting up along the way with capital H's, and then I can call this one H2 you know, and the previous one we can have called H1. Okay, so have H2. Yep. Stephen, go on.
Oh, K is equal to 2 or K is greater than 3.
Okay.
And then colon equals EQ or suck that thing of H double prime, I think.
Great, yeah. So if you look at where I am now, so I'm one step in from my previous step. So at the start, I knew that K was between 1 and 4. Now I know that K is between 2, aka 1 plus 1 and 4. So I'm running the same iteration again, but I'm starting at 2 this time. So I'm splitting up into K equals 2, or K is at least 3. Maybe this would all look prettier if I used 2 rather than 1 plus 1 here, which I think is perfectly fine. Okay. So here I am, K is 2, or K is at least 3. And this is looking quite a lot like where I was before. So what should be my next step this time? Another obtain. Great. So now I've got the or statement. K is 2, or K is at least 3. And I'm going to split on that. Same syntax, just on H2 rather than H1. Okay. And now I have 2 cases. In one case, K is known to be 2, and in the other case, K is at least 3. And again, one of these is already pretty close to the second case of the main interval cases. I could get there exactly by running a subst H primed on the equality in that case. And I'm left with one goal, which is to prove the fact for 2, namely 2 divides 12. Okay, so I've made pretty good progress. I used to have a lower bound of 1. Now coming back down to here, I've got a lower bound of 3. So I'll give you a couple of minutes to iterate further. When you've got a lower bound of 5 and an upper bound of 4, you'll have reached the point where I feel like we should do something different. So see if you can get to the point where we have a lower bound of 5. And at that point, we should be able to finish off by different methods.
Well, no, at this point, I have to stop it and say,
If you get rid of the solid and just
I
left
have
just
to-
by
writing a
all, it still
iterate
works.
the.
no,
I guess
not
it
at all. I'm just saying.
By the way, I think I know why we had difficulties. It's because we found that there was in
No,
that
I
one
wrote the first
exercise.
one.
Okay.
Yeah, no, it's still.
I mean, if you were able to circulate.
What I was impressed by is it
She
knew.
independently deleted those.
So if you could-
okay.
Four.
It's a conflict.
You see, it's not smart enough to stop.
Even
Now it's
though we
like, I
could
don't know.
modify it in the exact same way.
Yeah, okay.
Yeah. You want to- I don't know, what do you want? I don't know what you want.
Yeah, I'm having people like write it all out before time to make.
Because the 6 and the 4.
6, 4, and 3 is yeah. I mean,
It's one thing to increment the 2 and the 3 and the 4.
yeah. But yeah,
It had enough content.
Like I tried to just like they make the same kind of argument. With even with the use 12.
so first of all, in general, my suggestion is never do something if you have an error in the line before. So you see that he's complaining about 4H1. If you don't want to fix this part, just put sorry.
So it's just, but I don't want it to go.
Error messages.
No, I do want.
It says,
Okay, so
about that.
you can work on it
H1 is
later,
right,
but
it's H.
if you have a red squiggle, don't keep on work. You can fix
Yeah, I
it
didn't
very
even
quickly
notice.
with sorry, but don't ignore the red
And now
squiggle
it goes
because
to
it
5.
messes them and
No, that's at that point.
sometimes you end up with very strange also.
Everybody has.
It's very dumb, but
Yeah, but in a useful way, yeah.
Find out.
You know what, you put a misalign.
So you say.
Just the same thing.
It's a funny way to code. When it's frustrating, it turns off.
So. I feel like, oh, yeah, often when it's on.
Which I'm also having a little
But
bit.
then.
So I'm not sure which team. So we're trying to say, do the case that K was 3 is less than 3 is less than 2, which is kind of interesting because
Then the fourth state. K is like, K is 0,
Okay,
1.
so let's finish off our iteration here. We have 2 more steps. So firstly, let's do the step where we go from a lower bound of 3 to a lower bound of 4. So in this case, I'm going to call it H3, that either you're exactly 3 or you're at least 4. And I'll split these in the same way.
Both K equal 1 and here is 1 equal K.
And then I'll do it all again to say either you're exactly 4 or you're at least 5.
To see both of, so I wanted to see both of them here to see the difference. And now you see the difference is clear. Look at only the first part. You have.
And now comes the time to do something different. So you can see that at this stage, I've got these 4 stories, which are actually corresponding to the 4 cases produced by the original tactic. The original tactic that we're trying to replicate produces these 4 goals of showing that 1 divides 12, 2 divides 12 through to 4 divides 12. And those are exactly the 4 cases corresponding to these 4 stories that I'm leaving here. So we're doing everything done by interval cases, but leaving as sorry the steps you do after that. But there's a little bit more because we now need to do the final step, which is to convince Lean that when you get to the point that K is at least 5, having previously known that K is no more than 4, there's nothing more to do. Anyone want to try to explain to me why that's the case? Yeah.
You should be able to get that K is less than itself. And then I think there's a method, LT false, that says that like A less than A is false, and then you can eliminate that.
Right, so we need some kind of contradiction. So we can find somehow a proof that K is, less than itself, which is a contradiction. I was personally thinking of a slightly different method where we would, for example, prove 2 contradictory statements, P and not P, and get a contradiction from there, which is much the same as your one, given that we always know X is equal to X. Did you have another idea?
Instead of H4 things, we can, at this point, we can prove K is 4 because we have antisymmetry.
So you're right that we could do the special handling here rather than wait till it's after, but for secret reasons, based on how I want to write the tactic in the end, it will be more convenient for me to finish the last case by getting into the impossible situation and drawing a contradiction, rather than, as of course, as you say, is quite possible by, in this case here, seeing that I already know enough to restrict myself to the K equals 4 case. So let's go about building a contradiction. There are several different ways of doing this, but the contradiction I propose to draw is to observe that we now know enough to get that 5 is less than or equal to 4 by combining 2 known hypotheses. And at the same time, it should be pretty easy to prove that 5 is not less than or equal to 4. Those 2 jointly form a contradiction. So let's see, I can chain together using the transitivity of the less than or equal to relation, the fact that 5 is less than or equal to K, and the fact that K is less than or equal to 4. And that gives me a new hypothesis. 5 is less than or equal to 4. Okay. Lean, on the other hand, is pretty good at dumb numeric things, so I can just directly state it's not true that 5 is less than or equal to 4. And there's various automation. We saw norm num last week. Decide has a somewhat overlapping scope. At this point, I've got my contradiction, not quite the same as the contradiction that Colby was identifying, but comparable. And I can really just say, hey, Lane, I proved two contradictory facts. You know, this case is not possible. Questions? Yes.
What is the decide tactic used?
Decide invokes it proves decidable things, which is not, you know, I guess maybe very instructive, but sort of all facts about sort of arithmetic and inequalities and equalities on the natural numbers are what's called decidable. And it just, you know, invokes the actual algorithm for deciding, you know, the truth or falsehood of such facts. I know that's not very instructive, but I mean, by comparison, this would not work over the reals, because the real numbers, you know, are represented as equivalence classes of sequence, you know, Cauchy sequences, and that's not a decidable theory. So last week we would have used norm num for this. I'm using decide because that will be easier for tactic writing where possible, but you can think of this as kind of overlapping with norm num in that it checks facts about explicit objects. Do we have other questions? Okay.
Decide reasonably efficient. I know you said usually efficiency isn't too big of a concern, but is it reasonable?
I'll qualify that statement to you privately later, but decide is certainly plenty fast enough to prove facts about small natural numbers.
Parenthesis 5 less than 4.
Oh, this is the not sign. This is the negation logical operator. Yeah. So, you know, it's like, you know, we have this one for or and this one for and this one is for not. So this is the kind of situation where you start thinking about writing a tactic, because clearly we did the same thing over and over and over again. And you can tell from context how many times is the right number of things to do it over and over again, because the point is the algorithm is something like you start at the lower bound and you keep on doing this until you reach the upper bound and then you derive the contradiction to finish. So tomorrow someone might give you a problem where the range, you know, you've got on K is that it's between 7 and 3000. And if the range you've got on K is between 7 and 3000, it's not going to be fun to write it all out this way. But the algorithm is still perfectly possible, and you can see if you did have to write it all out, how it would work. This is when we start writing tactics. So the tactic is somehow going to build all this stuff under the hood for us. Questions? And this is basically what the interval cases tactic up here is doing. Okay, so that's sort of the beginning of our introduction to tactic writing. Let me see how I'm doing on time. So I've been going for 45 minutes at this point. So, yeah, Ellie.
Contradiction is also by design choice. Maybe we can, after we have this, we can just say by contra and apply the second this in the first one.
Well, I mean, yeah. Yes, there are several variants of this, and in fact, we'll get down to an even simpler version shortly.
Yeah, but I mean, like you said in the H4, seeing the contradiction at the end is also for tactic design.
No, I mean, I feel like it's quite, I like tactics to reflect what we do on paper, and I think it's quite common on a paper proof to say, ta-da, by contradiction, we're finished. So I think it's not so unidiomatic to do it this way. So here's, I guess, the next piece. So we've still written this proof in terms of tactics, but what a tactic is doing under the hood is it's building a so-called proof term. A proof term is a tree of lemmas inserted into each other in the right way to constitute a proof. So really, we're going to have to translate this proof slightly into term mode in order to understand what the tactic will really be doing. So I think for the last 15 minutes of today, I'm going to talk about term mode. And then starting next lecture, we'll actually start to build, you know, the tactic itself. So let's talk a little bit about term mode, which I think we didn't get a chance to discuss last week. Maybe a good place to start. Let's see. Maybe a good place to start is with this contradiction. So there is a lemma in Lean that is being used here. And in Lean, you can often, in the middle of a proof state, look inside what is happening, what proof term is being constructed by writing show underscore term. So let's try that here. So this is a little bit complicated because of this exposed names, which I think we can forget. But this contradiction is too complicated. But you can see.
If you don't use these for all the assumption, exposed names will probably go away.
Yeah, okay. That's a good idea. Okay. So let me do two things. Let me call this one by a nice new name like H and see what happens. Okay. That's a bit better. Okay. So this is what the contradiction is building. It is building a proof term. This part from here on is the proof term. And as you can see, the leading lemma is this lemma called absurd. So let's see what the absurd lemma says. This is, from the good old, reductio ad absurdum. This is a lemma saying, probably one of the first lemmas in the library. If you know both A and not A, then anything follows. And that's what we're using here in our proof by contradiction. So in this case, we are successfully proving both that 5 is less than or equal to 4 and that 5 is not less than or equal to 4. So absurd takes these two slots for the A and the not A. Use my new colors.
A little bigger.
Oh, really? Is it too small? Okay. This part here is going to be a proof of the negation of 5 less than or equal to 4. And when I build those up, this whole thing is going to be a proof of anything I like, where in this case, the anything I like is going to be the fact that K divides 12. Okay. Now we need to ask how Lean came up with these two pieces. So the 5 less than or equal to 4 is this H here. So this H is our proof that 5 is less than or equal to 4, and that too is a proof term. It really is the LE trans lemma applied to two pieces. Maybe I'll make this a bit bigger. So in this case, the two pieces are a proof of so this H double primed was the fact that 5 is less than or equal to K. And this part was a proof that K less than or equal to 4. So this LE trans lemma is the lemma saying the transitivity of the less than or equal to relation. If A is less than or equal to B, B is less than or equal to C, then A is less than or equal to C. So this, once we finish constructing it, goes into this slot of the absurd lemma. And likewise, we need to build something that goes into this slot of the absurd lemma. And we keep on going all the way down. And in the end, we'll come up with this sort of nested, huge nested chain of lemmas that is called the proof term associated to the proof we're building. And these tactics, you know, contradiction and decide and obtain and have are all involved in building the proof term. So let's take another step back. I'd forgotten that contradiction actually does decide for us if needed, so I didn't need this line here. Contradiction is filling in for itself what decide is doing. So maybe I'll just say that this part here, you know, builds in, you know, I won't read it too closely, but decidability is sort of special case. So you can think of this in terms of the proof term framework too, but it's a little bit complicated. So let's go back into our construction of the proof that k is less than or equal to 5, k is less than or equal to 4, and the fact that k is greater than or equal to 5. So one of these, it's easy to explain how we know it. Anyone want to tell me which of these is easy? The second one. So we've known this ever since the start. This was the k less than or equal to 4 fact given us from H2. The fact that k is greater than or equal to 5 is a bit more complicated. So we know that because we're in the second of two cases associated to this H4 here. So we at some point previously had built up that k was equal to 4 or k was less than or equal to 5. And this obtain here actually also builds up a proof term. So let me write separately about the piece of the proof term that is being constructed by obtain. So in the case of obtain, there is a lemma about OR that is called OR.elin, which I think is what's being used by obtain. And let's check what this OR.elin does. So it says, say you have three statements A, B, and C. You know A or B. You know that A implies C, and you know that B implies C. And the statement is that those three things together allow you to conclude C. So this OR.elin that is being implicitly used here at this obtain step here takes 3 slots. And let's try to explain what those 3 slots will be. So this OR.elin is going to construct a proof that k divides 12, subject to, firstly, a proof that k is 4 or k is at least 5. Secondly, a proof of this fact. Oh, thank you. Secondly, a proof of this fact given that k is 4. So proof that if k equals 4, then k divides 12. And thirdly, a proof that if k is at least 5, then k divides 12. So working on this piece here, given that k at least 5 implies k divides 12, actually led us into this whole branch of the proof term, which is now revealed as actually only one branch of the bigger proof term, which we started constructing here at the obtain line. And up and up and up and up it goes. By the time you have finished analyzing the whole proof, you'll have a huge tree, which we can actually inspect now. I'll show it to you. If I type show term on the whole thing, you can see that this is the whole proof term that gets constructed by the tactic. And it's actually not so far. You can see actually they use or dot cases on rather than or dot a lim, but the lemmas are nearly the same, so don't worry about that. You can see that, like with us, you know, it nests and it seems to do the same thing over and over again. We have an or dot cases on H1, blah, 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 blah. A little bit later inside that, we've got an or dot cases on H2. Then there's an or dot cases on H3 inside of that. And so in the end, we end up with this absurd term, which we were previously analyzing, which is one little piece of the or dot cases on H4, which itself is one little piece of the or dot cases on H3, and so on, going back to the beginning. So the tactics are letting you construct this proof term. And in this case, we still have these 4 sorries left, which later we're going to present to the user as goals. But it's perfectly possible to build a proof term that has some gaps. That's in fact what most tactics do. And then the gaps that are left in the proof term, you know, this is therefore like a partial proof, are precisely what is presented to the user saying, I made the transformation of the problem that you asked for, now keep working. So let me do one more thing. I think I have time for one more thing. Let me dig into this obtain and show how to do the same line without using obtain, but instead invoking this or.alim lemma that I was talking about. So going a step further towards writing this all by hand, as the tactic will need to do. So if I wanted to do this without using the obtain tactic and instead just going back to lemmas, what I would do is I would say, I have this nice or.elim lemma, and I'm going to apply it to this H4 I just wrote. And I'm going to use that to prove the goals. So maybe I would just say, apply or.elim H4. And now you can see that when I've done that, I've got these 2 bits showing that if k is 4, then the goal holds, and showing that if k is at least 5, then the goal holds. And in both of these cases, so I'm going to maybe write this using refine, which is a nice variant of apply. But the nice thing about this refine tactic is that it lets you be precise. That lets you be precise about the gaps you leave. The gaps are represented by these underscores. So we know that or.elim is going to take these 3 pieces, the proof of the or and the proof of the 2 implications, and I've left my 2 underscores to indicate that I still have work to do in filling in these 2 implications. And then there's a little bit more, so obtain is slightly smarter than that. It gets you to these goals with implications in them. We learned last time what tactic works on implications. Anyone remember? Intro. So I could be handling it in-house by saying, you know, intro H primed here, and by saying intro H double primed here, that would get me back to what obtain is doing. But let me also show you how to write the intro tactic, only in terms of proof terms. If you see an intro H primed, what that's doing on the level of proof terms is setting up a function that takes in H primed, a proof of the antecedent, and gives you out a proof of the goal. So
replace it with like a refine H maps to.
Yep. So this wraps the intro into my proof term as well. And I can do the same thing to get rid of this one here. So rather than having an intro H double primed in the second case, I can say fun H double primed maps to question mark. So this refine or.elim with the 2 funs shows what the obtain is doing as a sort of constructor of proof terms. And we'll sort of need to, in order to write a tactic, you know, just like we sort of unwrapped what contradiction is doing, maybe I'll write that here. Contradiction is really doing exact, absurd, H, and then this thing here. So that was really doing contradiction. So this is the proof term that contradiction built. This is the proof term that obtain built. At this stage, we can probably start next time with talking about how to build the whole thing in terms of tactics. But in order to write tactics, you need to have this information pretty much all the way through. You need to know what proof terms are being constructed by each piece of the proof style that you want to replicate. Okay, I think that's all for today. So after a short break, we will be discussing projects, trying to get people together into groups to work on their projects, selecting which projects different people want to work on. But we will pick this up tomorrow.
Question on the last point you made. So in a tactic, you described one thing you can do is like construct a whole proof term. Can you also just invoke other tactics?
You can. I find this is easier if the tactics you invoke are kind of low level. Like I find it easier to predict what my tactics are going to do if I invoke kind of low level tactics. But yeah, for example, when we later write a whole tactic that replicates this, I'm going to outsource the decide part by basically just calling the decide tactic. And I think also the subst part, I'm just going to call the subst tactic. So those are pretty low level. And I think I'm going to build the rest of this myself, but I'm going to call on the existing subst and decide tactics rather than writing those parts myself.